Okay, we're going to continue on. So we're talking about these cycloalkanes, which again will lose two hydrogens to close up the ring. So it does have the general formula CnH2n. They are named really the same way as our alkanes. We just put the cyclo in front of it to indicate that they have kind of closed up on each other and made a ring type structure. Um, and again, I would say probably most of the time you will probably see these guys oftentimes kind of drawn in the line structure formula. Again, if you needed to do some type of condensed, you would kind of write in, like the CH2s there at each of the points and stuff like that. Um, so why don't you take a moment here and give the all right, let's take a look. So you're going to count up carbons is always a good way to start. So there's one there, two, three, 4, 5, 6, 7, and 8. There's nothing else attached. So that's basically just 8 carbons in a row. And that would then give us octane, right? A base octa for 8, ANE because they are all single bonded. If we take a look here, we got 1, 2, 3, 4, and 5 carbons. So this is based off of pentane. It is not a straight chain of 5 carbons, but it's kind of closed up and made like a ring type structure. So we'll just put cyclo in front of that, and that would give us our cyclopentane. Any questions on those there? All right. And kind of went through some of these here, but we'll just kind of go through them again. We'll count carbons, always good place to start. 1, 2, 3, and 4. So again, on our first 10 alkanes, 4 carbons is butane, yeah, ANE, all single bonded. Taking a look at our triangle here, again, there is a carbon at each of those spots. So that is 3 carbons. So that is propane. Once again here, that is not just a straight run of 3 carbons, but it is kind of run into a ring type structure. So that would get us our cyclopropane in this case. Yeah. And just counting carbons, 1, 2, 3, 4, 5, 6, 7, and 8. So that again is going to be octane in this case, all single bonded. And lastly here, we got 1, 2, 3, 4, 5, and 6 carbons. So 6 carbons is based off of hexane, hexa for 6, right? And again, it is not a straight chain of 6, but it is a ring type of structure. So a little cyclo in front of that, and we got a cyclohexane. Any questions on any of those names there? All right, so now let's talk a little bit about what happens when we have substituents attached. Substituents are a fancy way of saying groups that are not part of the longest carbon chain. So earlier we talked about when you name something, really the first thing you do is find the longest continuous carbon chain that you don't back up on or anything like that. Go one way until you hit a dead end. So if there is something that is not part of that longest chain, that's known as a substituent. And it is referred to also as a group or an alkyl group. And our example here is the one we saw earlier. Here, if we just count it up, we got 4 in a row. And again, there is nothing else attached there, which would give us butane. As we talked about previously, in this arrangement of those 4 carbons, the longest carbon chain is actually 3. And again, remember, you can't get that 3 going in either direction, kind of straight across, or you could go this way and up to get the 3 as well. By the way, it does not matter if you have multiple ways you could find the longest carbon chain, which does happen. My recommendation would be just to take the straightest one, sometimes put a box around it, and sometimes easier to see everything else that's there. But technically, if you did the one that went up and over, you would end up with the same name. So it should end up the same. So in this case, this is our main chain here, which again is 3 carbon base, which is propane. So the main part of the chain here is propane as opposed to here, where we have 4 carbons And that obviously is just butane. Now, what we are left with, though, is a group that is not really part of that main chain. It is what is referred to as a group, and it is this guy right here, and that is a 1-carbon group. And this is a substituent, and this, because it is a carbon group, is sometimes referred to as a alkyl group. And that's sort of the big class of groups that are named there, carbon-based groups. So because it has only 3 hydrogens rather than 4, it is basically a group that is attached, but it only has 1 carbon, right? So if we think about 1 carbon in terms of alkanes, that is methane, right? Now, this group here has 1 carbon, but only 3 hydrogens, yeah? And the reason it only has 3 hydrogens is if I wanted to, for example, attach this methane to that group down here, and I put a bond like that, what happens to my methane now? It now has too many bonds, that carbon. It has now 5 bonds and 10 electrons. So what makes something a group and the ability for it to be a group is it will be missing a hydrogen. And where it's missing the hydrogen is where it's able to attach to the main carbon chain and still have the correct number of electrons and not have too many electrons. So instead of this being methane, ANE, which is an alkane, this is a alkyl group because it's carbon based. And by the way, alkyl ends in YL. So instead of methane, this is what is known as a methyl group, YL, yeah? Missing 1 hydrogen from the alkane, and at that hydrogen is where it attaches. And that allows it to attach to the main long carbon chain and not have too many electrons. So that is what is known as a methyl group, and that is why that is known, for example, as methylpropane. Sometimes people might call it 2-methylpropane, but it's methylpropane versus butane. They are different compounds, even though they're basically have the exact same formula. So as we talked about earlier, when you have this situation, these are what are known as isomers. So they both have the exact same formula, but different connectivities, and they actually are different things because of the way they're connected, even though they share the exact same number of carbons, the exact same number of hydrogens, and that is what an isomer is, basically. So structural isomers will have the same formula, but will be bonded differently. And because of that different sort of arrangement of those molecules in 3-dimensional space, essentially will create a different compound, even though it shares the exact same formula. So why don't you try to draw 3 isomers of pentane. So what we're looking for are 3 different compounds that have the formula C5 and H12. So take a moment and draw them. So the simplest one clearly would be just 5 in a row. Yeah, so that seems like a good one. So 1, 2, 3, 4, and 5. As we talked about earlier, we're looking for 4 bonds of carbon. So this guy would have 3 hydrogens. This guy has 2 lines, which would be 2 hydrogens. 2 lines, which would be 2 hydrogens. 2 lines would be 2 hydrogens, and 3 lines there, or 1 line, which would be 3 hydrogens. That obviously is a condensed formula. If you wanted to draw out all the hydrogens, that would be your structural formula in this case. All right, so I did 5 in a row, seemed good. So there's 1 down, 2 to go. We will then go maybe not 5 in a row, but maybe just do 4 in a row. Why not? Just take off 1, right? 1, 2, 3, 4. And then maybe move that 5th carbon somewhere in 1, right? So at this point, we would have 1 line to the end here, which needs 3 hydrogens. This guy to the left here has 3 lines, needs just 1 hydrogen. Guy at the bottom has 1 line, needs 3 hydrogens. Two lines needs two hydrogens, and one line there needs three hydrogens. So that's not too bad. Well, maybe we go three in a row. Why not? Just keep taking one off. 1, 2, 3. Maybe I put a carbon there, maybe a carbon there. I don't know. Let's see. We got three hydrogens there since it has one line. Three hydrogens there since it has one line. Three hydrogens there since it has one line. And maybe three hydrogens there since it has one line. And maybe I draw something like this. Or not that. Let's draw maybe I'll do this and maybe this. The three there. This guy needs two. This one needs one. Needs three hydrogens and three. And we'll just go with that. All right, so I drew a bunch here. Are these all isomers of each other? So the first thing we got to make sure is do they all have the same formula, right? So this guy here definitely has 5 carbons and 12 hydrogens. The second one there, 1, 2, 3, 4, 5 carbons, 3, 6, 7, 9, 12 hydrogens. So that's good. Next one, the bottom, 5 carbons, 3, 6, 9, 12 hydrogens. So that's good. 1, 2, 3, 4, 5 carbons. 3 and 2 is 5, and 6 and 9 and 12 hydrogens. So they all have the correct number. Are they all actually isomers of each other? The answer will come up in a second. We'll take a look. So let's finish talking about a couple things here, and then we'll come back and double check if I actually drew all those things correctly or not. So we've been talking about sort of substituents or groups that are attached in terms of how to name. And as I mentioned before, if it's a carbon-based group that's not part of the longest carbon chain, we do call that an alkyl group. And it's basically also named based off of the alkane name. Drop the A and E and put YL at the end. But one thing that does sometimes happen with groups is it does kind of depend, for example, how the carbon attaches and which carbon is attaching to the group. So when we look at a carbon, for example, here, we can classify a carbon based on how many other carbons it's attached to. So this center carbon is directly attached to how many other carbons? 1. This is what is known as a primary carbon. Yeah, it's basically a carbon attached to one carbon. Primary, like first grade, right? So like one, basically. And if we have this carbon in the center, it is directly attached to how many carbons? 2. This is what is known as a secondary carbon because it is attached 20. That'd be good. Secondary carbon here. So this is a primary carbon, a secondary carbon. And lastly, we can have a carbon that is attached directly to 3 other carbons. And because it's attached directly to 3 other carbons, this is what is known as a tertiary carbon. So we have primary carbons, secondary carbons, and tertiary carbons. Sometimes people are taught to identify the carbons by how many hydrogens there are. And that would be 3 hydrogens per primary, 1 hydrogen for tertiary. I personally just think carbon to carbon gives you the actual number. So if it's attached to 1, it's primary. If it's attached to 2 carbons, it's secondary. If it's attached to 3 carbons, it's tertiary. It's a much easier way to do that. So how can that affect, for example, a group sort of name? It does affect it based on whether or not it is like the primary carbon attaching or like a secondary carbon. And for example, if we looked at propane here, which has 3 carbons. Now, if I have propane missing one hydrogen, where it's going to attach in here at the end. It is now no longer propane, but it is a group, and this would be a propyl group. Yeah. So this would be a propyl group. By the way, the carbon where it's attaching is what type of carbon? That is this carbon right here is directly attached to how many carbons? Just one, yeah. So this is actually a primary carbon right here. The one that I box in the middle, by the way, is what type of carbon? It is a secondary. It's directly attached to a carbon on each side, which is 2 carbons, and that would be a secondary carbon. And this carbon right here would be a primary as well, right? So you could actually attach propane in as a group to either of the end carbons, and you get what is just referred to as a propyl group, or sometimes people call it end propyl for like normal propyl group type of thing. But propane has the ability to attach also through its secondary carbon. And if it attached through its secondary carbon, it would actually attach, say here, and it can attach at its secondary carbon. And this creates that CH3, CH3 group where the attachment again is happening at that secondary carbon. And this actually has a special name. This is what is known as isopropyl group. And that's a historical name that's still used today. And it's because it's not attaching at the end, which is a primary carbon. It's actually attaching through the secondary carbon. There are other groups, for example, which is known as a butyl group, right? Butyl group should have how many carbons? 4, based off of butane, right? So you have a butyl group, which is a butane molecule missing a hydrogen, and it just attached it to the end. There's also a group known as sec-butyl, which if you had to take a guess means that it is attaching through what type of carbon? One of its secondary carbons is where it's attaching. There's also a butyl group that's known as T-butyl. If you had to take a guess, that one's going to attach at the tertiary carbon as well. So there are different sort of groups that have some special names based on which carbon attaches. We don't use too much of sec-butyl or T-butyl. We do see isopropyl a lot in our sort of working here, but you can get sort of different sort of group names depending on which carbon is involved. Any questions on that there? Yeah.
What was it makes it isopropyl again?
This arrangement, this kind of a 3-pack of arrangement where you got like a CH3, a CH, and a CH3, and where the attachment kind of happens at that CH in the middle. That's what's referred to as like a nice little arrangement of it. The propyl part's because it's actually just 3 carbons. There's also isobutyl, which is similar, but it also has that kind of CH3, CH3 arrangement. Also has a CH2 in there as well, but it has that kind of arrangement. It's sort of was referred to as like an iso arrangement of it. Other questions? Now, we also, in addition to just carbon-based type of groups, very commonly in organic chemistry, we come across our group 7s, our halogens. And our halogens are typically named fluoral for if there's a fluorine attached, chloral if there's a chlorine attached, bromo if there's a bromine attached, and iodo if there is an iodine attached. So these are the common sort of names for those kind of halogen groups. Here's a table from your book, again, of some of those groups there. And as you can see here, there's our methyl or ethyl. You could again do it for anybody. There's some of those special ones, our isopropyl we talked about. Here's our isobutyl. Again, you could kind of see that CH3, CH3 arrangement with the extra kind of CH2 going on there. Again, here, this is a tertiary sort of carbon. I'm sorry, it's a secondary primary carbon that's attaching to, but it has this arrangement which makes it that isobutyl group. Again, T-butyl, which we don't do, is basically just a CH with 3 CH3s attached to it, so that gives it a tertiary type of thing. All right, so how does this help us? Well, this helps us with if we go to name alkanes that have stuff attached to it. So let's talk about sort of the process you want to follow when you want to name alkanes in the IUPAC way. So if you want to give kind of that official naming of alkanes, these are basically the steps that you want to follow. The first step always is find the longest continuous carbon chain. And you do want to make sure that you kind of just check all your options. So sometimes, like I said, it's not always the one that just goes straight across. Sometimes it goes straight and up and over. You do want to kind of check all your options. Whatever you find in that case, in terms of the longest carbon chain for us, will match one of those first 10 alkanes. So that will be your base of your name, right? So, if you had something like, let's see. So let's say we had something like this. So we'll see how bad I just did here making something up. Let's see. Hope I didn't go too many carbons I don't want. Let's see here, go there. We'll go here. We'll go here. We'll go here. All right. So longest carbon chain on this one is how much? That is a couple of different numbers. So let's see here. All right. So best piece of advice is just to go straight across and see, right? So we got 1, 2, 3, 4, 5, 6. So that seems not bad. Other option, right? We could go straight 1, 2, 3, 4, 5, 6, and 7. So that is longer. So that's going to be good. Other options, which probably won't be so great, but you could go 1, 2, 3, 4, which is obviously less. You could also go 1, 2, 3, 4, 5, which is less. And that's pretty much all your options, I think, in that case. So it does look like 7 is a winner here. And let me try to erase those without taking out everybody here. All right, so in this case, our longest carbon chain actually starts around here. 1, 2, 3, 4, 5, 6, and 7. So that is going to give us our base of our name, because 7 carbons, all single bonded, is heptane. So the base of our name is going to be heptane in this case, right? All right. So besides the longest carbon chain, we also have some groups that are attached in this case. And the 2 groups that we have attached is right here and right here, right? Now, each of those groups are carbon-based groups, which means we then want to find our groups that are attached. And each of those are 1 carbon groups, which means they are based off of methane, but because they're missing a hydrogen, they are methyl groups, right? So that's a methyl group, and that is a methyl group. Now, I happen to have, in this particular case, the same group, 2 of the same groups in that molecule, right? So we do use prefixes when that happens, and the prefix for 2 is di, just like we did with naming, right? So di, tri, tetra, maybe. So for 4. So in this case, those 2 groups together would be what are referred to as a dimethyl group, because there are 2 methyl groups in the entire compound. It doesn't matter if they're on different carbons. It doesn't matter if they happen to be on the same carbon. You just had 2 of them in that compound. By the way, if I had 3 of them, it would be a trimethyl and so forth, or a tetramethyl, or whatever it may be. All right. So once we have the longest carbon chain, once we sort of figure out our names of our groups here, what we do is number the longest carbon chain to give the groups the smallest numbers. So you want to number the longest carbon chain. And the goal here is to give, in this case, these two groups the smallest numbers of what carbon they're at. What we're basically doing when we name something is just telling everybody, hey, if you come over here to this carbon, you're going to find this, right? Come to carbon 4, this is where this group will be. This group's over there at carbon 6 or whatever it may be. So you really always have kind of two ways of numbering. You could number, for example, in this case, left to right, which would mean this is carbon 1, this is carbon 2, that's carbon 3, that's carbon 4, that's carbon 5, that's carbon 6, and that's carbon 7. So going in the red direction, right? My groups end up at which two carbons? My groups end up at carbon number 4 and carbon number 5 in this case, yeah? So those are where my two groups end up, right? Carbon 4 is where this guy's at, and carbon 5 is where this group is at. Now, the other option is you could number, in this case, right to left. So we'll go, I'll go blue with it. Why not? That's good. We'll go carbon 1 here, carbon 2 there, carbon 3 there, carbon 4 there, carbon 5 there, carbon 6 there, carbon 7 there. Going in the blue direction, my two groups end up at which two carbons? Carbon number 3 and carbon number 4, yeah? So these are your two options. So here's the deal. It is as simple as the first number looking at which one is smaller. 3 is smaller than 4, right? So 3 beats 4, which means the correct way of numbering is the blue direction. You want to go with the smaller number. So we would want to go in this case with our blue numbering. That means that technically speaking, we'll get rid of our red numbering in this case since we don't really want it. We have a methyl group that's hanging out at carbon number 3. This would be 3-methyl. By the way, we put a dash between a number and a letter. And this guy would be 4-methyl basically here. And again, we put a dash between a number and a letter. So we do go a dash between a number and a letter, or between a letter and a number, we do a dash. If you happen to have two numbers in a row, you do a comma between the two numbers. So these are some other sort of things to add in there. All right, now that we figured out where our groups are located, and we also figured out the main chain, the last thing that we do is name it, and we put our groups in alphabetical order, ignoring the prefix. So we do ignore the prefix here, but we do put it in alphabetical order. If we had more than one different group, in this particular case, and the one I made up, we actually don't have different groups. So for example, if we had an ethyl group and a methyl group, when we go to name it, we would put the ethyl first, followed by the methyl name, regardless of the numbering. So you just can go alphabetical based on the name, regardless of the numbering. So the ethyl group could actually have a higher number, but still come first because alphabetically it comes before, obviously, M in terms of that. All right, so to put this all together here, we're going to go with our numbers, which are 3, 4. Because those are both methyl groups, we do need to give both numbers. We then need a dash dimethyl because that is telling us at carbon 3 there's a methyl group, and at carbon 4 there's a methyl group, and there's 2 total methyl groups in the compound, which is why it's called dimethyl in this case. And the last part of the name is heptane. Yeah. So this would be 3,4-dimethyl heptane in this case. So longest carbon chain gives you the base of the name. You want to then find what the names of all your groups are attached. You then want to number the longest chain to give those groups the smallest number. By the way, if there is a tie in terms of numbering, like it doesn't matter which way you go, the next thing that you would want to go look at is, although it doesn't matter which way I go in terms of the numbers, you would then want to go alphabetically, which one would give the smaller numbers. So, it may come from smallest numbers, and then if it's kind of a tie, they're both say like 3 and 4 or something like that, you then would want to go whichever one's alphabetically coming first, you would want to give the smaller number to. So sometimes that does happen as well. Any questions on that? All right. So we're going to go back now to our isomers here. And now that we understand hopefully how to kind of go through the naming, the best way to know whether or not you drew an actual isomer and did not draw the same thing is to name it correctly. And if you end up with a different name and you named it correctly, you drew an isomer. If you end up with the same name, and even though it looks different than the previous one you drew basically the same thing over again. So let's see how that works here. We're going to come here, right? Longest carbon chain straight across is 5. There's absolutely nothing else attached, right? So this is straight up pentane, right? So that is pentane in this case. All right. You give the name for this one. Take a moment and give the proper. Okay, let's take a look at this one here. Longest carbon chain on this one is 4. 1, 2, 3, 4. You could also get 4, obviously, going this way. 1, 2, 3, 4. It really doesn't matter, honestly, which one you choose. I, again, would probably take the straight one, so we'll go that way. So right off the bat, with 4 carbons in a row as our longest carbon chain, we know the base of our name should be butane, right? So now we want to look and see what is attached that's not part of those 4 carbons. And in this particular case, we got this guy right here, which is a 1 carbon group. And that also is based off of our alkane. So 1 carbon is methane. And because this is a group, this is now a methyl group, right? And at this point, we then want to number our longest chain. You could probably just see it from looking at it, but we'll do both. You could go 1, 2, 3, and 4, and going in that direction, my group is going to be at carbon number 3. The other option would be to number it in the other direction, which will give me 1, 2, 3, and 4. And once again, going in the red direction here is going to give me a smaller number for our group. And that's always what gets the priority here in terms of alkanes. It's the group, but you want to give it the smaller number. So we would want to go in this direction. And because that's at carbon number 2, that means this is not just a methyl group, but this is a 2-methyl. So a 2-methyl. At that point, that's all we need to give the name. And I'm just going to go up with the name. So this would be 2-methyl, and this would be butane in this case, right? So 2-methyl butane would be the name. First off, any questions on how I got to that name there? Yeah. It is actually, yeah. So it is one word. So really you wouldn't have too much spacing going on in alkane names. You will have some dashes in between the groups and stuff like that. But kind of that last part of the name, that last group in terms of alphabetical will run into the alkane name. Other questions? All right, so in order for this to be an isomer, it should have a different name, does it? So I did okay on that. So that is an isomer. So pentane and 2-methyl butane are isomers of each other. So let's hit this one next, give this guy a name and see what you come up with. Multiple ways, which you could go straight, you could go up, you could go down. You can actually just go straight down the middle if you want as well. We'll give you 3. So 3 is our longest carbon chain. So that tells us the base of this name is going to be propane. We then have a methyl group there, right? And a methyl group there. So each of those are 1 carbon groups. And because we have 2 methyl groups within this compound, we do need to use our prefix of di for that. So we basically got like a dimethyl sort of happening here. Now, in this case, Doesn't matter which way you go, you're going to end up with 1, 2, 3, 1, 2, 3, right? No matter which way you go, it's a tie. In this case, they're both methyl groups. So that's going to give us a 2, 2. You do have to give the number twice, even if it's the same number and they're on the same carbon. Again, you can just thank those three guys there at the IUPAC for making that up. And you want a dash. So that's everything we need in this case. This is going to be here 2, 2 dimethyl and propane. Yeah. Any question on that name? By the way, is that a different name than the other two? So is it an isomer? It is. So far, not too bad. I could almost pass. Let's see how I did on my last one. All right, let's do this one together since we're towards the end. Longest carbon chain on this one is... It is 1, 2, 3, and 4. Yeah. Again, continuous carbon chain. So that is 4 carbons. You could get 3 going that way. You could also get 4 going that way if you like. So 4 looks like a winner in terms of our longest carbon chain. So something with 4 carbons is going to have a base of a name of butane, right? I then will have this guy, which is a methyl group, right? And if I number this left to right, 1, 2, 3, 4, or I go kind of starting at the bottom, 1, 2, 3, 4, which way should I number it? What number should I use for the methyl group? Yeah, this gives it the smaller number, which is 2. So that would be 2 methyl. Putting that together, that would be 2 methyl butane. Did I see that name before? I did. That's this guy over here, even though it may look different, right? Is that guy an isomer? It is not. It's the exact same thing. So that is not an isomer. It's actually the same one as the second one I drew. So again, just by kind of moving something down or up, sometimes people think they drew something different. Best way to check yourself is to give everybody the proper name. And if you do like I just did there, end up with 2 that are the same, you basically just made it look different and they're not different compounds. Any questions on that there? All right, we'll lay that up.